What keeps me moving is building this flip clock, and it is being moved forward by its motors and gears. Today I want to tell you everything about electric motors and gears I learned so far. We will begin with... So, let's start with a simple electric motor. It's basically some coils put together in a clever way, creating magnetic fields that get flipped over and over again, pushing away from magnets and making it spin. When I plug it in, the motor spins. Great! This is a DC motor, meaning direct current motor, and they are the most basic ones. Though you can find control boards to adjust the rotational speed, like in this turntable. But now, if I attach a plate to it and start to spin it, I just have no idea how far it goes. I just can't return it right in position. Feels like a gamble. There has to be something better. Good for us, others had the same problems before and they created stepper motors. I have here the 24BYJ48, the most basic stepper motor you can get. Often it even comes with a control board. The control board delivers electric pulses in a specific pattern provided by the microcontroller. This allows the stepper motor to do small, defined fractions of a turn called steps, thus a stepper motor. These motors have 1024 steps for one 360-degree rotation. And this can be done precisely, again and again, just like a clock. But, just like a clock, it can still be off. Though every step takes 1 second, which is controlled by this microcontroller, it is not synced up. In other words, the microcontroller doesn't know the motor position. That is something for that we need Initialization allows the controller to have a repeatable initial motor position. I solved it with a reflective infrared emitter and sensor, which detects the lighter background showing through the notch. The motor is then stopped by the microcontroller, but now knows the exact position and can make precise turns to a position. I also tried a Hall effect sensor, which can detect magnetic fields, but then I need a magnet in my gear, which limits the thickness. And the readily available modules don't have a potentiometer to adjust the sensitivity, unlike the infrared modules. All this allows me to orientate the motor, move it around and reinitialize it if necessary. To bring it together, I just need one final thing I needed to assemble my clock is where to put the drive. In the end, I used a simple spur gear that puts the motor out of reach of the flaps. One additional advantage is that the gearing allows me to change the rotational speed of a driven flap gear. But remember, if your drive gear has 4 times the tooth count of a driven gear, then it has 4 times the rotational speed, but now also only a quarter of the torque. For me, to make the programming and relations easier, I started with whole numbers for the gear ratio. And I based it on the step count of a motor. So, 1024 divided into 4 elements with 256 steps each that get split into 20 flap positions, which each are 16 steps wide. You can also use uneven ratios, but then the turns depend on more than a simple step count rule in your code. On the other hand, you enable more flaps on a gear, for example, if you want to put an alphabet on it. Put together, I have this motor and gear assembly to drive my flip clock. In any case, I'll be off finishing the other parts of the final flip clock version. If you enjoyed this video, subscribe, like and leave a comment if you want a deep dive into one of the topics. See you soon!